Out there, in the endless dark of the cosmos, lurk monsters so powerful they can twist the fabric of space itself. Black holes, nature's most enigmatic and terrifying marvels, shroud themselves in mystery, swallowing light, warping time, and defying everything we think we know about physics. But what if I told you the most fascinating black holes aren't the ones close enough to study? They're the ones so far away, their light has traveled for billions of years just to reach us. These are the universe's most distant black holes, ancient relics from a time when the cosmos was young, and their secrets could rewrite our understanding of existence. Picture this, a single speck of light, barely visible through the most powerful telescopes, carrying a message from the edge of time. That faint glow isn't just a star, it's the scream of matter being torn apart, a supermassive black hole feasting in the darkness 13 billion years ago. To put that into perspective, that light began its journey when the universe was just a toddler, before Earth, before the Milky Way, before even the first galaxies fully formed. And yet, here we are, catching whispers of these cosmic titans as if decoding a letter from the dawn of creation. That's the magic of distant black holes. They're not just holes in space, they're time capsules, each one holding clues about how the universe grew, how galaxies were born, and how the laws of physics pushed to their extremes. Over the next few minutes, we're diving deep into 30 mind-bending facts about these faraway giants. We'll explore how they defy logic, how they shape the cosmos, and why spotting one is like finding a fossil from the universe's infancy. So buckle up, we're about to journey to the farthest edges of space and time, where the impossible becomes real, and the oldest monsters in existence are waiting to be discovered. Let's start with a cosmic record breaker, the farthest black hole ever detected. Meet ULAS J1342+0928, a name that might not roll off the tongue, but this quasar holds a staggering title, the most distant supermassive black hole we've ever spotted. Nestled over 13 billion light-years away, its light began traveling toward us when the universe was barely 690 million years old, just a fraction of its current age. Now, here's what makes this discovery mind-blowing. Black holes this massive shouldn't exist so early in cosmic history. By the time we see ULAS J1342, it's already packing the mass of 800 million suns. That's like finding a skyscraper in the middle of the Stone Age. It defies logic. How did it grow so big, so fast? Scientists are still piecing together the puzzle, but one thing's clear. This ancient monster challenges everything we thought we knew about black hole formation. Think about the sheer effort it took to detect it. The signal from this quasar is so faint, it's like trying to spot a single firefly from across an ocean. Yet, by combining infrared data from telescopes like the WM Keck Observatory and the Atacama Large Millimeter Array, astronomers caught its telltale glow, the last whispers of a feast. Because that's what quasars are, supermassive black holes in their most violent phase, shredding surrounding gas and blazing with enough energy to outshine entire galaxies. ULAS J1342 isn't just a distant dot, it's a time machine. Its light carries chemical fingerprints revealing a universe still emerging from its dark ages, when the first stars and galaxies were still flickering to life. And here's the kicker. Its existence suggests there were plenty of these giants lurking in the early cosmos, hidden in the shadows. If we keep searching, who knows what else we'll uncover about the universe's wild, untamed youth. Spotting a black hole billions of light-years away isn't just about pointing a telescope at the night sky and hoping for the best. It's more like cosmic detective work, piecing together clues from the faintest whispers of light that have traveled across the universe since its infancy. One of the most crucial tools in this hunt, redshift, a phenomenon so fundamental to astronomy, it's practically the universe's way of leaving breadcrumbs for us to follow. When light from a distant object travels through the expanding cosmos, its wavelengths stretch, shifting toward the red end of the spectrum. The farther away the object, the more extreme this redshift becomes. For black holes like ULAS J1342, this shift is so dramatic their light arrives as infrared, invisible to human eyes but detectable by instruments like the James Webb Space Telescope. By measuring redshift, astronomers can calculate not just the distance to these ancient monsters, but also how long their light has been traveling. It's like finding a letter with a faded postmark and realizing it was sent before paper was even invented. But light alone doesn't tell the whole story. Enter quasars, the beacons of the black hole world. These are supermassive black holes in their most ravenous phase, surrounded by swirling disks of superheated gas that glow brightly enough to outshine entire galaxies. As material spirals inward, it emits bursts of X-rays, ultraviolet light, and even radio waves, creating a multi-wavelength signature that's hard to miss. Telescopes like Chandra and XMM Newton specialize in capturing these high-energy fingerprints, allowing scientists to pinpoint black holes even when they're buried in the cosmic dark ages. And sometimes the universe hands us a lucky break: gravitational lensing. When a massive object like a galaxy cluster sits between us and a distant quasar, its gravity bends and magnifies the quasar's light, acting like a natural telescope. This cosmic magnifying glass can amplify faint signals by factors of 10 or more, turning an impossible detection into a clear snapshot. It's how we've spotted some of the most distant black holes lurking behind intervening galaxies, their light warped into eerie, elongated arcs. Yet, even with all these tools, finding these ancient giants remains a triumph of persistence and ingenuity. Astronomers sift through mountains of data, cross-referencing observations across different wavelengths, ruling out imposters like distant stars or supernova. Each confirmed detection is a time capsule, carrying secrets about the universe's most violent and formative eras, and proving that even in the deepest reaches of space, nothing stays hidden forever. Quasars are the universe's ultimate lighthouses, blazing beacons cutting through the cosmic dark, powered by supermassive black holes in their most ferocious feeding phases. Imagine a single object so bright it outshines an entire galaxy, visible clear across the observable universe. That's the sheer power of a quasar. At their core lies a supermassive black hole, millions to billions of times the mass of our Sun, surrounded by a swirling disk of superheated gas. As matter spirals inward at nearly the speed of light, friction heats it to millions of degrees, unleashing torrents of energy across the spectrum, from X-rays to radio waves. This makes quasars detectable even when their host galaxies are too faint to see. What's truly staggering is how quasars solve one of astronomy's greatest challenges: observing the unobservable. Black holes themselves emit no light, but quasars turn them into cosmic searchlights. Take the quasar J1342+0928, whose light has traveled over 13 billion years to reach us. Without its surrounding gas screaming in X-rays and ultraviolet as it's devoured, we'd have no hope of spotting its central black hole. It's like hearing a lion's roar in a pitch-black jungle. You might not see the predator, but you know exactly where it's lurking. These brilliant phenomena also serve as timestamps. The light from distant quasars carries telltale signatures of the early universe's composition. By analyzing their spectra, astronomers have discovered clouds of primordial gas from just 800 million years after the Big Bang, pristine material untouched by star formation. Some quasars even cast shadows, their light absorbed by intervening gas clouds that reveal the universe's growing structure. It's as if each quasar is a flashlight illuminating different chapters of cosmic history. Yet quasars aren't just passive signposts. Their intense radiation shapes entire galaxies. Outflows from these feeding black holes can blow away star-forming gas, effectively putting the brakes on a galaxy's growth. Some theories suggest this feedback mechanism explains why we don't see galaxies larger than those observed. the very monsters that power quasars might also be keeping their homes from growing too massive. It's a cosmic balancing act of destruction and regulation, written in light across billions of years. The most mind-bending part, we're likely only seeing a fraction of these cosmic beacons. For every quasar visible today, there could be hundreds more obscured by dust or angled away from Earth. New infrared telescopes like the James Webb Space Telescope are peeling back these dusty veils, revealing black holes that were previously invisible. Each discovery rewrites our understanding of how these giants grew so quickly in the universe's youth, and what role they played in lighting up the cosmic dark ages for good. The light reaching us from these distant black holes isn't just a signal, it's a message from the past, carrying secrets from a younger, wilder universe. Every time astronomers detect one of these ancient giants, they're not just observing space, they're stepping into a cosmic time machine. Take the black hole at the heart of Quasar J1342+0928, whose light has been traveling for 12.8 billion years. When that glow began its journey, the universe was less than 700 million years old, an era when the first galaxies were still clumping together from primordial gas. By the time that light reaches our telescopes, entire civilizations could rise and fall on Earth, and yet for the black hole, only an instant has passed. That's the strange magic of relativity and distance. We're seeing these objects not as they are, but as they were when the cosmos was practically a newborn. What makes these observations so extraordinary is how they reveal the universe in its most chaotic phase. When we look at nearby black holes like Sagittarius, a star at the Milky Way center, we're studying mature systems that have settled into relative quiet. But the distant ones, they're caught in the act of formation, gorging on gas in a universe dense with raw material. Their light shows us environments with 10 times more heavy elements than predicted, suggesting star formation was already in overdrive. It's like comparing a calm adult to a toddler mid-tantrum. The energy, the violence, the sheer unpredictability are all laid bare. Some of these black holes even challenge our timelines. GNZ11, a galaxy hosting one of the oldest known supermassive black holes, existed when the universe was just 400 million years old. Conventional models say such monsters should take billions of years to form, yet there they are, fully grown in cosmic terms practically overnight. It's like finding a 5-year-old who's already 6 feet tall. This forces scientists to reconsider how black holes could have grown so rapidly, with theories ranging from gargantuan direct collapse black holes born from collapsing gas clouds to mergers of countless smaller holes in densely packed early galaxies. The time travel effect doesn't stop at distance. Gravitational lensing, where closer galaxies bend the light of more distant objects, can magnify these ancient black holes while also creating multiple images of the same quasar, each showing it at slightly different times. In rare cases, we might see the same black hole in 2 epochs simultaneously, like a cosmic flipbook. It's as if the universe itself is giving us a curated exhibit of its own history, with black holes as the starring artifacts. Yet the most humbling realization isn't just how far back we're seeing, it's how much we're missing. For every distant black hole we detect, countless others remain hidden behind veils of dust or point their beams of light away from Earth. The James Webb Space Telescope is now revealing some of these shy giants, but each new discovery raises more questions than answers. What we're witnessing isn't just a snapshot of the past, it's a puzzle that forces us to rethink how quickly structures emerged in the young universe, and what role these ravenous, time-bending monsters played in shaping everything that followed. Measuring the mass of a black hole billions of light-years away is like trying to weigh a shadow. It shouldn't be possible, yet astronomers have devised ingenious ways to do it. The challenge starts with distance. When a black hole sits 13 billion light-years from Earth, its features blur into a single pixel of light. No telescope, no matter how powerful, can resolve the event horizon or directly observe its gravitational pull. So how do we weigh these cosmic ghosts? The answer lies in reading the frantic dance of matter around them. Take quasars, for instance. These luminous beasts betray their black holes' masses through their accretion disks, the swirling rings of superheated gas doomed to be devoured. As material spirals inward at near light speed, it emits radiation with a distinctive fingerprint. By analyzing the widths of specific emission lines in the quasar spectrum, scientists can gauge the gas's velocity. Faster orbits mean stronger gravity and thus a more massive black hole anchoring the system. It's like listening to the pitch of a singer's voice to guess their height. The deeper the gravitational well, the more extreme the motions around it. But there's a catch. These measurements assume the accretion disk is viewed at a particular angle. If we're seeing it edge on, dust clouds might obscure parts of the disk, skewing the data. That's why astronomers cross-check with other methods like reverberation mapping. Here, they monitor time delays between fluctuations in the quasar's light, say, a bright flash in the disk's inner edge and a corresponding echo in its outer regions. The lag reveals the disk size and, combined with velocity data, pinpoints the black hole's mass with surprising precision. It's cosmic echolocation, using light instead of sound to map the invisible. Sometimes the universe lends a hand through gravitational lensing. When a massive galaxy bends the light of a distant quasar, it creates multiple images of the same object. Tiny variations in brightness between these copies can hint at the black hole's mass, as its gravity subtly distorts the lensed light. It's as if the cosmos provides a funhouse mirror, warping reflections just enough to betray the monster's size. Yet even with these techniques, uncertainties linger. Some distant black holes appear too massive for their age, defying models of cosmic growth. Others flicker erratically, suggesting chaotic feeding patterns that complicate measurements. Each discovery tightens the margin of error, but also uncovers new puzzles like why certain quasars weigh 10 billion suns while others from the same era are mere featherweights. The scales of the cosmos are far from ordinary, and every measurement pushes our understanding of how these titans came to rule the early universe. One of the most baffling mysteries in modern astrophysics isn't just that distant black holes exist, it's how absurdly massive some of them became in what seems like the blink of a cosmic eye. Conventional wisdom suggests black holes grow slowly, feeding on gas and stars over billions of years, but the early universe didn't get the memo. Take the quasar Ton 618, for instance. When astronomers first measured its mass, they were stunned. This beast tips the scales at 66 billion times the mass of our Sun. And here's the kicker: it achieved this colossal size when the universe was less than 1 billion years old. That's like finding a sequoia tree sprouting to full height overnight in a freshly tilled garden. So how did these early monsters bulk up so fast? One radical theory involves direct collapse black holes, primordial giants born not from dying stars but from the catastrophic collapse of vast gas clouds in the early universe. Picture a nebula so dense and massive that instead of fragmenting into stars, it implodes directly into a black hole with the weight of 100,000 suns. These cosmic shortcuts could have given black holes a head start, allowing them to reach supermassive sizes while the universe was still in diapers. But there's another twist: the environment of the early cosmos might have been a black hole buffet. Back then, space was smaller, denser, and packed with raw material. Galaxies collided more frequently, funneling gas into central black holes at breakneck speeds. Simulations show that in this chaotic nursery, mergers between smaller black holes could have created supermassive titans in just a few 100 million years. It's the difference between dining at a quiet cafe and an all-you-can-eat rush at a galactic food court. Yet even these explanations have holes. Some of the largest distant black holes are found in what should have been cosmic deserts, regions too sparse to feed such rapid growth. This has led to wilder ideas like primordial black holes left over from the Big Bang itself, or exotic physics that allowed black holes to supercharge their growth through mechanisms we haven't discovered yet. Every new observation seems to add another layer to the puzzle, proving that the early universe played by rules we're only beginning to glimpse. What's truly humbling is how these ancient giants force us to rethink time itself. We're used to cosmic evolution unfolding at a stately pace, but the existence of supermassive black holes in the infant universe screams that something extraordinary, something we haven't fully imagined, was at work. Whether it's hidden physics, freakish cosmic conditions, or an entirely new chapter in black hole formation, one thing's clear: the universe's first black holes didn't just grow. They exploded onto the scene like uninvited titans, rewriting the story of how structure emerged in the cosmos and leaving us scrambling to catch up. In the cosmic rulebook for black holes, there's a law that was supposed to be ironclad: the Eddington limit. This fundamental principle states that a black hole can only grow so fast before the radiation pressure from its own feeding frenzy pushes material away. Think of it like trying to drink from a fire hose. The harder you suck, the more water blasts back in your face. For a black hole, this limit means it shouldn't be able to guzzle matter faster than the equivalent of a few suns per year. Yet when we peer across billions of light-years at quasars like ULAS J1342+0928, we find black holes clearly breaking this speed limit, some by factors of 10 or more. The math behind the Eddington limit is elegant in its simplicity. As gas spirals toward a black hole's event horizon, it heats up and emits radiation. Past a certain point, that radiation becomes so intense it blows incoming material outward, creating a balance between inflow and outflow. For a 10 billion solar mass black hole, this equilibrium should cap its growth at roughly 1 solar mass every 10,000 years. But the distant universe laughs at such constraints. The quasar H1346+0228, observed when the cosmos was just 800 million years old, shows a black hole that somehow packed on billions of solar masses in a fraction of that time. How do these ancient monsters cheat the system? One possibility is they gorged on cold, dense gas streams that could slip past radiation barriers, like sneaking spoonfuls of ice cream when no one's looking. Another theory suggests magnetic fields acted as cosmic funnels, directing materials straight into the black hole's maw while bypassing the usual pressure buildup. Some simulations even show super Eddington phases where black holes temporarily swallow entire stars whole, their gravity overwhelming any outgoing radiation. But the real curveball comes from recent observations of lensed quasars. By studying magnified images of distant black holes, astronomers have spotted some accreting matter at hundreds of times the Eddington limit for millions of years straight. This isn't temporary gluttony, it's a systematic flouting of what we thought were nature's rules. Perhaps the early universe's thicker gas reservoirs allowed for sustained feeding frenzies impossible in today's sparse cosmos. Or maybe we're seeing evidence of entirely new physics, where quantum effects or extra dimensions play unexpected roles in black hole growth. What makes this mystery so thrilling is how it turns textbook astrophysics on its head. The Eddington limit wasn't just some rough guideline, it was considered as fundamental as the speed of light for black hole behavior. Yet these distant overachievers prove our models are incomplete, hinting at growth mechanisms we've barely begun to imagine. Every time we catch one of these ancient black holes in the act of breaking the rules, we're not just learning about the past, we're getting front-row seats to a cosmic revolution rewriting the laws themselves. The universe has a secret conversation happening between black holes and the galaxies they call home, an intricate dance of destruction and creation that shapes cosmic evolution. Supermassive black holes aren't just passive occupants at the centers of galaxies. They're active architects sculpting their surroundings with forces so powerful they can halt star formation or ignite it anew. And when we study the most distant black holes, we're witnessing this relationship in its rawest, most volatile form, a time when both galaxies and their central monsters were figuring out how to coexist. Consider the quasar HLFS3, a galaxy from just 800 million years after the Big Bang. Its central black hole, already a billion solar masses, blasts out enough energy to heat surrounding gas to millions of degrees, literally pushing potential star material away like a cosmic leaf blower. Yet paradoxically, this same fury can trigger star birth farther out, where shockwaves compress gas clouds into stellar nurseries. It's a feedback loop of chaos. Too close to the black hole and gas gets vaporized, just the right distance away, and it collapses into stars. Distant quasars like this reveal how early galaxies grew in fits and starts, their fates tied to the tantrums of their ravenous cores. But here's where it gets stranger. The most massive modern galaxies, like our Milky Way, have black holes whose masses eerily match the mass of their surrounding stars. This correlation suggests an almost symbiotic relationship, as if galaxies and their black holes grew up together, regulating each other's size. Yet when we look at ancient black holes like the one in galaxy COS 9927, which existed when the universe was under 1 billion years old, they're often disproportionately massive compared to their host galaxies. It's like finding a toddler with the muscles of a bodybuilder, hinting that black holes might have grown first, with galaxies playing catch-up. Distant black holes also expose the violent birth of galactic structure. Take the protocluster around Quasars J1342+0928, a sprawling web of galaxies anchored by a supermassive black hole. Its intense radiation seems to have acted like a gravitational lighthouse, pulling in gas and smaller galaxies to form one of the universe's first large-scale structures. Without these early black holes, the cosmos might have remained a formless soup of gas, never clumping into the grand designs we see today. Yet the biggest revelation might be what we don't see. Some early galaxies host black holes suspiciously quiet for their size, suggesting they gorged early and then went dormant. Others lack central black holes entirely, implying they formed through different rules. This diversity tells us galaxy formation wasn't a single recipe but a messy experiment, one where black holes were sometimes the chefs, sometimes the ingredients, and occasionally the unexpected guests who took over the kitchen. The farther back we look, the clearer it becomes. To understand how galaxies grew up, we have to grapple with the monsters in their cores. The birth of the universe's first black holes is one of cosmology's greatest unsolved puzzles, a mystery that forces us to rewrite the rules of how these monsters come to life. Conventional black holes, like the ones we see today, form when massive stars collapse under their own gravity at the end of their lives. But when we peer back to the universe's infancy, that process doesn't add up. The earliest stars, known as population 3 stars, were made of pure hydrogen and helium, lacking the heavier elements that help modern stars shed mass through stellar winds. Without that release valve, these primordial giants should have burned hot and fast, ending as black holes no larger than a few hundred solar masses. Yet the distant quasars we observe tell a different story. Supermassive black holes, billions of times heavier than the Sun, already in place when the cosmos was barely a toddler. This glaring mismatch has led scientists to propose a radical alternative: direct collapse black holes. Imagine a cloud of pristine gas in the early universe, so dense and massive that instead of fragmenting into stars, it implodes directly into a black hole with the weight of 100,000 suns. No star death, no supernova, just a cosmic shortcut to a monster. These hypothetical giants could have formed in regions bathed in intense ultraviolet light, which prevented the gas from cooling and splitting into smaller clumps. Like a pressure cooker set to cosmic extremes, these conditions would have forced entire gas clouds to collapse into singularities almost overnight, seeding the universe with black holes ready to grow. But there's a twist. Some simulations suggest the first black holes might not have needed such exotic origins. In the frenzied environment of the early cosmos, where galaxies collided and merged constantly, smaller black holes could have rapidly combined into supermassive titans. Picture a mosh pit of stellar remnants, each collision funneling more mass into a central beast. Add in dense gas inflows, rivers of raw material streaming into galactic centers, and you have a recipe for explosive growth. Yet both theories have holes. Direct collapse requires near-perfect conditions, gas clouds free of turbulence, bathed in just the right amount of radiation. Meanwhile, the stellar remnant path struggles to explain how black holes grew so massive so quickly, even with ideal feeding conditions. This has sparked wilder ideas, like primordial black holes forged in the chaos of the Big Bang itself. Relics so ancient they predate stars entirely. Some theories even suggest these early black holes could have been shaped by quantum effects or extra dimensions, physics we've yet to fully grasp. What's astonishing isn't just the scale of the mystery, but how it forces us to rethink cosmic timelines. The existence of billion solar, mass black holes in the universe's first billion years is like finding a fully grown oak tree in a freshly planted garden. Whether through freakish collapses, voracious mergers, or entirely unknown mechanisms, one thing is clear: the universe's first black holes didn't play by the rules we know today. And every new observation, every flicker of light from the edge of time brings us closer to rewriting the story of how these titans came to rule the cosmos. Dark matter, the universe's most elusive architect, might hold the key to one of the biggest mysteries about distant black holes, how they grew so massive so fast. We can't see it, we can't touch it, yet this invisible substance makes up 85% of the universe's matter, sculpting galaxies and bending the fabric of space itself. Now, scientists are piecing together a startling possibility. Dark matter didn't just shape the cosmos around black holes, it might have supercharged their growth in ways we're only beginning to understand. Picture the early universe as a vast construction site, with dark matter acting as the scaffolding. Its gravitational pull drew ordinary gas into dense clumps, creating the perfect nurseries for galaxies and their central black holes. But here's where things get wild. Some theories suggest dark matter could have done more than just set the table. In regions where it clustered especially tight, its gravity might have funneled gas directly into black holes at rates far beyond what's possible under normal physics. Imagine a cosmic slip and slide, where dark matter's invisible hands shove entire rivers of gas into a black hole's maw, bypassing the usual speed limits. Evidence for this comes from eerie correlations. Distant quasars, like the one in galaxy J1342+0928, often sit at the crossroads of dark matter filaments, massive, web-like structures that stretch across the cosmos. Simulations show these intersections are black hole buffets where gas flows converge in chaotic frenzy. Even more telling, some ultra-distant black holes are found in what should have been cosmic deserts, regions too sparse to feed such rapid growth. Unless, of course, dark matter was secretly stockpiling fuel there all along. Yet the plot thickens. A handful of researchers speculate that certain types of dark matter might not just assist black holes, they could become them. Hypothetical particles called weakly interacting massive particles, or WIMP, could theoretically clump so densely they collapse into black holes without any stars involved. Others propose primordial black holes, tiny, ancient ones formed in the Big Bang's aftermath, might actually be dark matter in disguise. If true, the very substance holding galaxies together could be made of microscopic black holes, a twist that would rewrite cosmology itself. The hunt for answers is pushing telescopes to their limits. Projects like the Vera Rubin Observatory are mapping dark matter's cosmic web in unprecedented detail, while the James Webb Space Telescope peers at ancient quasars, searching for telltale signs of dark matter's gravitational fingerprints. Each observation is a piece of the puzzle, hinting at a deeper, stranger relationship between the universe's most mysterious substance and its most destructive forces. One thing's clear: if dark matter truly played midwife to these ancient black holes, then the story of cosmic evolution is far stranger and more interconnected than we ever imagined. Gravitational lensing is one of the universe's most elegant tricks, a natural magnifying glass that bends the very fabric of space to reveal what should be invisible. When a massive object like a galaxy cluster sits between us and a distant black hole, its gravity warps the fabric of space-time, bending the light traveling around it like a prism distorting a beam of sunlight. The result, a faint, ancient black hole suddenly becomes visible, its light twisted into glowing arcs or multiplied into ghostly duplicates. It's as if the cosmos itself is handing astronomers a telescope more powerful than anything we could build. Take the quasar QS02237+0305, nicknamed the Einstein Cross for its perfect quadruple image. The light from this 12-billion-year-old black hole splits into 4 distinct points as it passes through a foreground galaxy, creating a cosmic mirage. Without this lensing effect, the quasar would be far too dim to detect with even our most advanced instruments. But gravity's distortion doesn't just amplify the light, it also lets scientists weigh the black hole indirectly. By measuring how the lensed images flicker in tandem, astronomers can calculate the mass of both the foreground galaxy and the distant quasar, turning a single observation into a treasure trove of data. But lensing isn't just about magnification. The distortions themselves carry secrets. When light from a black hole bends around a galaxy cluster, subtle anomalies in the warped image can reveal hidden structures. Dark matter halos, satellite galaxies, even other black holes lurking along the line of sight. In 2018, the Hubble Space Telescope spotted lensed images of the quasar J1342+0928, stretched into a near-perfect ring, with tiny kinks in its symmetry betraying the presence of an entire unseen galaxy. It's like reading the ripples in a pond to map the pebbles beneath the surface. The most astonishing lensed black holes push beyond mere detection. Some, like the quasar IPTF16JULY, appear to flicker at different times in each lensed copy, a delay caused by light taking slightly different paths around the lens. These time delays act as cosmic stopwatches, letting astronomers measure the expansion rate of the universe itself. Others, like those in the galaxy cluster MSC SJ0717, show multiple black holes lensed at once, offering a comparative snapshot of black hole growth across cosmic epochs. Yet perhaps the most tantalizing lensing discoveries are the ones we haven't made yet. Statistically, there should be thousands of distant black holes currently being lensed by foreground galaxies, their light bent just enough to slip past our detection thresholds. New observatories like the Vera Rubin Observatory are scanning the sky for these elusive arcs and rings, each one a potential window into the universe's first billion years. What we've seen so far might just be the prelude, a handful of scattered clues hinting at legions of ancient monsters waiting in the bent light, their stories frozen in spacetime's funhouse mirrors. The cosmic dawn wasn't just the birth of light, it was the awakening of chaos. Picture a universe still cooling from the Big Bang, shrouded in darkness so thick that hydrogen atoms floated like ghosts in an endless void. Then, somewhere in that abyss, the first stars flickered to life, their searing ultraviolet radiation ripping apart the neutral gas around them in an epoch called reionization. This was the universe's first sunrise, and at its heart, black holes already lurking, already hungry. What's staggering is how quickly these monsters emerged. The earliest known quasar, ULAS J1342+0928, blazed into existence just 690 million years after the Big Bang, so early that some of the first stars might still have been burning when its light began the 13-billion-year journey to our telescopes. This wasn't just a black hole, it was a pioneer carving its home from the raw materials of a universe still learning how to build galaxies. The cosmic dawn wasn't a gentle transition, it was a revolution, and black holes were its shock troops. Their role was paradoxical. On one hand, their radiation helped ionize the universe, stripping electrons from atoms and making space transparent to light, a process crucial for the cosmos we know. Yet their ferocious energy also sterilized entire regions, blowing away the gas needed to form new stars. In galaxy SB2, observed at just 800 million years old, the central black hole's jets have cleared a bubble of emptiness spanning thousands of light years, a cosmic dead zone where star formation was snuffed out before it could begin. But these ancient black holes also acted as cosmic lighthouses. Their quasars' piercing light illuminates the structure of the early universe like a flashlight beam cutting through fog. When astronomers analyzed the spectrum of Quasar J1342, they found shadows cast by primordial hydrogen clouds, fossils from the darkness before stars. Other quasars reveal patches of lingering neutral gas, regions where the cosmic dawn hadn't yet fully broken. Without these distant black holes, we'd be blind to the universe's murky adolescence. The real surprise, some of these early black holes might have predated the galaxies around them. Simulations suggest direct collapse black holes could have formed in dark matter halos before stars lit up their surroundings, meaning the first light in the universe might not have come from stars at all, but from the glowing disks of black holes devouring gas in the darkness. It's a radical rewrite of cosmic history, not a dawn of gentle starlight, but the violent sparking of engines that would shape everything to come. What's humbling is how much remains hidden. For every quasar we've spotted from the cosmic dawn, there are likely hundreds more obscured by dust or drowned out by younger stars. But with each new observation, each ancient black hole pulled from the shadows, we're piecing together the untold story of how darkness first gave way to light, and how the hungriest objects in existence helped build the universe we call home. The most baffling thing about the universe's oldest black holes isn't that they exist, it's how they managed to bulk up to unimaginable sizes before the cosmos had even finished its morning coffee. Take the quasar ULAS J1342+0928, a supermassive black hole tipping the scales at 12 billion solar masses. Here's the kicker: it achieved this staggering weight by the time the universe was just 900 million years old. That's like finding a fully grown blue whale in a kiddie pool. It shouldn't be possible under the rules we know. So how did these early monsters break the cosmic speed limit? One leading theory involves something called supermassive star seeds. In the primordial universe, before heavy elements existed, clouds of pure hydrogen and helium could have collapsed directly into stars with masses up to 100,000 times that of our Sun. These freakish, short-lived giants would have exploded as hypernova, leaving behind black hole seeds already thousands of times more massive than the ones formed by modern stellar collapses. It's the difference between starting a fire with a spark and starting it with a barrel of gasoline. But even these super seeds don't fully explain the speedrun. Enter chaotic accretion, a feeding frenzy unlike anything seen today. The early universe was denser, with gas packed so tightly around young galaxies that black holes could gorge continuously without the usual interruptions. Simulations show that under these conditions, a black hole could devour gas at rates hundreds of times faster than the theoretical maximum, like a cosmic version of competitive eating where the rules don't apply. The smoking gun might lie in the way these ancient black holes ate. Modern black holes typically consume gas in orderly, rotating disks, but the earliest ones may have feasted through spherical accretion, swallowing matter from all directions at once. This free-for-all buffet would have eliminated bottlenecks, allowing for exponential growth. Evidence comes from the quasar ULAS J1342+0641, whose light spectrum suggests it was surrounded by a turbulent, multidirectional gas flow rather than a neat disk. Yet the most tantalizing clue comes from an unexpected place: dark matter halos. The largest distant black holes are consistently found at the centers of galaxies with exceptionally massive dark matter reservoirs. Some theorists suggest these invisible structures acted like cosmic conveyor belts, funneling gas into black holes at rates that bypassed normal physical limits. It's as if the universe's hidden scaffolding handed these early monsters a cheat code to growth. The implications are staggering. If black holes could grow this rapidly in the cosmic dawn, it means our understanding of gravity, accretion physics, or even dark matter might be missing key pieces. Every time we discover another ultramassive black hole from the universe's first billion years, it's not just a new record, it's a challenge to everything we thought we knew about how cosmic structures emerge. And with the James Webb Space Telescope now peering deeper than ever into this era, we're on the verge of either solving this puzzle or realizing it's far stranger than we ever imagined. Mergers might be the universe's ultimate cheat code for building supermassive black holes at breakneck speed. In today's cosmos, black hole collisions are rare spectacles. Think of the gravitational waves detected from events like GW 150914, where two stellar mass black holes spiraled together over eons. But rewind to the early universe and the rules changed entirely. Space was smaller, denser, and packed with young galaxies crashing into each other like bumper cars. In this chaos, black holes didn't just merge, they formed catastrophic traffic jams of gravity where dozens could slam together in a cosmic blink. Take the protocluster around Quasar SDSS J1342+1018, a swirling metropolis of infant galaxies observed just 770 million years after the Big Bang. Simulations suggest its central black hole, already weighing 1 billion suns, could have grown through chains of mergers, each collision adding another zero to its mass tally. Picture a snowball rolling downhill, except instead of snow, it's swallowing entire black holes the size of solar systems. The math gets dizzying. If every major galaxy collision deposited just one intermediate black hole into the core, a supermassive monster could assemble in under 500 million years. But mergers alone can't explain everything. Even in ideal conditions, there's a bottleneck: the final parsec problem. When two black holes get close, they often stall just light years apart, circling endlessly unless some external force kicks them over the finish line. In the early universe, that nudge might have come from dense gas clouds or third black holes acting as gravitational matchmakers. The quasar POX128 at the heart of a colliding galaxy pair shows exactly this. Its surrounding chaos of gas and stars likely forced its central black holes to merge faster than physics normally allows. The smoking gun: some distant quasars flicker with odd brightness patterns, like J03-1-0718, whose light curve suggests not one but two supermassive black holes wrestling in its core before merging. Others, like COSMOS J1007+0227, leave behind telltale jets bent at bizarre angles, a cosmic fingerprint of merger-induced spin. Even gravitational wave detectors might soon catch echoes of these ancient collisions, if models are right that the early universe rang with black hole mergers at frequencies we've yet to detect. Yet for all their violence, mergers have an elegant side effect: they're cosmic recycling plants. Every collision flings stars and gas outward, seeding future generations of star formation while the central black hole grows fatter. It's a paradox: the same process that builds monsters also helps build the galaxies around them. And that might be the ultimate clue to why the earliest supermassive black holes seem to defy logic. They weren't just growing, they were rewriting the rules, turning the universe's chaotic youth into an all-you-can-eat buffet of gravity, gas, and sheer cosmic audacity. Observing black holes at the edge of the observable universe is like trying to read a postcard from across a football stadium while someone waves a flashlight in your eyes. The light from these ancient monsters is staggeringly faint, stretched by cosmic expansion into near-invisible infrared wavelengths, and often drowned out by closer galaxies or interstellar dust. For decades, even our most advanced telescopes hit a brick wall when probing beyond 12 billion light-years until now. Enter the James Webb Space Telescope, a game-changer in the hunt for these cosmic relics. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb's infrared eyes are tailor-made to catch the stretched, reddened glow of the universe's most distant black holes. Its 18 hexagonal mirrors working together collect 6 times more light than Hubble could, acting like a cosmic zoom lens for the early universe. Already, Webb has shattered records. In 2023, it confirmed the existence of Quasar J1342+0928, a black hole blazing just 700 million years after the Big Bang, a detection that would have been impossible with previous technology. But Webb isn't alone in pushing boundaries. The upcoming Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will map the sky with a field of view 100 times wider than Hubble's, scanning for rare lensed quasars hidden in cosmic crowds. Meanwhile, ground-based giants like the extremely large telescope in Chile, with its 39-meter mirror, will dissect the light from these objects in unprecedented detail, revealing the chemistry of gas clouds swirling around black holes in the universe's toddler years. The challenges aren't just about distance. Ancient black holes often lurk behind thick curtains of dust, their light scrambled by eons of traveling through evolving galaxies. Radio telescopes like the Square Kilometre Array will tackle this by mapping the faint whispers of hydrogen gas distorted by black hole gravity, while gravitational wave detectors like LISA could one day sense the ripples from mergers in the cosmic dawn. Each tool fills a gap, turning what was once noise into a symphony of data. Yet the revolution isn't just in hardware, it's in how we process the flood of information. Machine learning now sifts through terabytes of telescope data, flagging oddities that human eyes might miss. In 2022, an algorithm scanning old Hubble images discovered a supermassive black hole hidden in plain sight, its light bent into a near-perfect ring by a foreground galaxy. These tools are rewriting the playbook, proving that sometimes the key to finding the universe's oldest monsters lies not just in building bigger telescopes, but in teaching them to see differently. What's thrilling is how much remains uncharted. For every distant black hole Webb spots, statistical models suggest there are dozens more lurking just beyond detection, each one a potential Rosetta Stone for understanding how the cosmos grew up. As these telescopes peer deeper, they're not just showing us black holes, they're handing us a time machine frame by frame, revealing an era when the universe was wild, young, and ruled by giants we're only beginning to comprehend. The hunt for ever older black holes isn't just about breaking records, it's a race to rewrite cosmic history. Right now, the most distant confirmed black hole, ULAS J1342+0928, sits at a staggering 13 billion light-years away. But astronomers are convinced that's just the beginning. Hidden deeper in the cosmic fog, beyond the reach of current telescopes, could lurk black holes from the universe's first 200 million years, an era so primordial it predates even the formation of the first stars. Finding one would be like uncovering a fossil from the universe's birth cry. Why push further? Because the earlier we spot a black hole, the more it challenges our models of cosmic evolution. Current theories suggest the first stars ignited around 180 million years after the Big Bang, and their death seeded the earliest stellar black holes. But to grow into the billion solar mass monsters we see soon after, they'd need impossibly efficient feeding. Unless, of course, black holes existed before stars, a possibility that's sending teams scrambling to design instruments capable of peering into that uncharted era. Projects like the James Webb Space Telescope's deep field surveys are already targeting patches of sky where the odds of spotting these pioneers are highest. scanning for the faint infrared glows of quasars that shouldn't exist yet. The implications of success would ripple across astronomy. A black hole dating to the universe's first 150 million years would force us to reconsider everything from dark matter's role in early structure formation to the very nature of gravity itself. Some theories even suggest such objects could be primordial black holes relics forged in the Big Bang's furnace, not from dying stars. Others speculate they might reveal exotic physics, like black holes born from collapsing dark matter or extra-dimensional weirdness we've yet to imagine. But the search is a needle in a haystack challenge. At these distances, even quasars are dimmer than a candle on the moon, and their light is often obscured by thick cosmic dust. New techniques are emerging to tackle this. Machine learning algorithms sift through telescope data for the unique signatures of ancient black holes, while teams combine observations across radio, X-ray, and infrared to filter out false positives. Gravitational lensing, too, is becoming a key tool, with astronomers using galaxy clusters as natural magnifying glasses to amplify whispers from the edge of time. The next breakthrough might come from an unexpected direction. Radio telescopes like the Square Kilometre Array could detect the faint hum of hydrogen gas swirling around black holes in the cosmic dawn, while future gravitational wave observatories might catch echoes of mergers from that epoch. Every new instrument brings us closer to answering the ultimate question. Did black holes shape the universe from its very first moments, or were they latecomers to a cosmos already in motion? The hunt isn't just for a record, it's for the missing chapter in the story of how everything began. Quasars don't just shine, they obliterate every notion of cosmic scale with their sheer, unfathomable energy. Picture an object no larger than our solar system, yet blazing with the brightness of 1,000 Milky Ways combined. That's the raw power of a quasar in its prime, fueled by a supermassive black hole devouring matter at a rate that defies physics as we know it. The numbers are dizzying. The most luminous quasars pump out over 10 trillion times the energy of our Sun, enough to outshine every star in their host galaxies for millions of years. And here's the kicker, that light isn't just visible. It floods the cosmos with X-rays, gamma rays, and radio waves, a full-spectrum scream from the edge of spacetime. Take the quasar 3C273, one of the first ever discovered. Its brilliance is so intense that if you placed it where our Sun sits, the sheer radiation would vaporize Earth in seconds. Yet this monster sits 3 billion light-years away, its light diluted by cosmic distance to a mere pinprick in our telescopes. Even so, astronomers calculate it emits enough energy every hour to power human civilization for millennia. And 3C273 isn't even among the most extreme quasars like S5001-4+813 dwarf it by factors of 10, their jets punching holes through intergalactic space like cosmic blowtorches. But where does all this energy come from? The secret lies in the black hole's frenzied feast. As gas spirals toward the event horizon at nearly light speed, friction heats it to millions of degrees, transforming it into a swirling maelstrom of plasma. In this chaotic dance, matter doesn't just vanish, it's shredded apart. Its kinetic energy converted into radiation with mind-bending efficiency. Einstein's equation E=mc² isn't just theory here, it's the engine behind the universe's most powerful dynamos. A single kilogram of matter falling into a quasar's black hole can release 10 times the energy of a nuclear bomb, and quasars swallow mountains of material every second. Oddly, this violence has a cosmic silver lining. Quasar radiation helped reionize the early universe, stripping electrons from atoms and making space transparent to light. Their jets carve vast bubbles in intergalactic gas, creating nurseries for future galaxies. Even their death throes seed the cosmos. When quasars exhaust their fuel and fade, the heavy elements forged in their accretion disks spread outward, becoming the building blocks for planets and life. So while these distant monsters might seem like agents of destruction, they're also the unseen architects of the universe we inhabit today, proof that even the most terrifying forces in existence can shape the cosmos in ways we're only beginning to understand. The universe wasn't born transparent. It spent its first few 100 million years shrouded in a thick fog of neutral hydrogen, a cosmic dark age where light couldn't travel far without being swallowed. Then something extraordinary happened. The fog lifted and the cosmos became the glittering expanse we know today. This pivotal moment, called reionization, remains one of astronomy's greatest mysteries, but mounting evidence suggests quasars, those ravenous black holes blazing at the universe's edge, might have been the match that lit the fire. Think of reionization like ice melting across a frozen lake. The neutral hydrogen atoms filling the early universe acted like countless tiny ice cubes, absorbing ultraviolet light and keeping space opaque. To clear the fog, something had to rip electrons from those atoms, a process requiring staggering amounts of energy. For decades, scientists assumed the first stars were the sole culprits, their fierce UV radiation slowly carving bubbles of transparency. But when astronomers studied quasars like ULAS J1342, they found a problem. These black holes were pumping out enough X-rays and ultraviolet light to ionize hydrogen across vast cosmic distances, long before stars alone could have done the job. Here's where it gets wild. Quasar radiation didn't just ionize hydrogen, it did it with brutal efficiency. Simulations show a single quasar could clear a sphere of transparency spanning millions of light years, its high-energy photons acting like cosmic blowtorches. The quasar J1342+0928, observed just 700 million years after the Big Bang, sits at the center of such a bubble, a void in the neutral hydrogen fog so large it defies explanations involving only stars. Even more telling, the pockets of lingering neutral gas around it align perfectly with models where quasars spearheaded reionization in their regions, leaving patchwork shadows of the fading cosmic dark age. But quasars didn't work alone. Their jets, twin beams of plasma moving at near light speed, punched through intergalactic space, shocking surrounding gas into ionized superheated waves. In galaxy protoclusters like ULAS J1342+0928, these jets stretch for hundreds of thousands of light years, leaving behind trail markers of reionization's progress. It's as if the universe's first black holes weren't just passive participants in this transformation, they were demolition crews, tearing down the opaque walls of the cosmic dark ages with beams of raw energy. Yet the story isn't so simple. Some regions of the early universe reionized earlier than others, and certain quasars seem too short-lived to explain the scale of the clearing. This has led to a provocative idea. Maybe quasars triggered reionization by jump-starting star formation in their host galaxies, creating a feedback loop where black holes and stars worked in tandem. The quasar HS1549, for instance, sits amid a frenzy of young stars, its radiation potentially compressing nearby gas clouds until they collapsed into stellar nurseries. Those new stars then contributed their own UV light, accelerating the ionization process like a cosmic chain reaction. What's at stake isn't just a history lesson. If quasars played a major role in reionization, it means black holes didn't just grow in the early universe, they shaped its very structure. Their light determined where and when galaxies could form, which regions remained transparent, and ultimately how the cosmos became the star-filled expanse we see today. It's a humbling thought. The same monsters that devour stars might also have been the midwives of cosmic dawn, their terrifying energy somehow paving the way for everything that followed. The next decade promises to revolutionize our understanding of distant black holes, with an arsenal of cutting-edge telescopes and missions poised to peel back cosmic mysteries we've barely begun to glimpse. Leading the charge is the Nancy Grace Roman Space Telescope, set to launch in 2027. With a field of view 100 times wider than Hubble's, Roman will conduct sweeping infrared surveys capable of spotting thousands of previously hidden quasars at the edge of time. Its unprecedented sky coverage acts like a cosmic net, trawling for the rarest and most ancient black holes, ones that might reveal how the first structures in the universe took shape. But Roman won't work alone. The European Space Agency's Athena X-ray Observatory, launching in the mid-2030s, will peer through the dust veils shrouding early black holes, detecting their high-energy screams as they devour matter. Where optical and infrared telescopes see only faint glows, Athena's advanced spectrometers will measure the chemistry, temperature, and motion of gas swirling into these gravitational traps. Picture an interstellar forensic lab reconstructing cosmic crimes from the faintest X-ray fingerprints. Meanwhile, on the ground, the extremely large telescope's 39-meter mirror, nearly 4 times wider than today's largest optical telescopes, will dissect the light from ancient quasars in exquisite detail. Its instruments, like Andes, could detect the faint whispers of oxygen or carbon in billion-year-old gas clouds, clues to how black holes polluted the early universe with heavy elements. And when paired with the square-kilometer array's radio eyes, we'll have our first true multi-wavelength portrait of black holes from the cosmic dawn. Perhaps the most revolutionary tool isn't a telescope at all, but a gravitational wave detector. LISA, the Laser Interferometer Space Antenna, will float in orbit as a trio of spacecraft firing lasers across millions of miles. Unlike ground-based detectors limited to high-frequency waves from stellar mass black holes, LISA's sensitivity to low-frequency ripples could catch the mergers of supermassive black holes in the early universe, events that would otherwise leave no trace in light. It's like hearing the footsteps of monsters that vanished before telescopes existed. The real game-changer, AI-powered discovery. Machine learning algorithms already sift through petabytes of telescope data, flagging oddities human eyes might miss. Future systems trained on simulated universes could predict where the rarest black holes hide, guiding telescopes like cosmic bloodhounds. And with quantum computing on the horizon, we might soon model black hole growth with accuracy impossible today, unraveling how they defied physics to dominate the young cosmos. What's at stake isn't just more data, it's paradigm shifts. Every time we push observational boundaries, distant black holes surprise us. Maybe the next breakthrough will be a black hole from the universe's first 100 million years, or evidence of dark matter-fueled growth, or even a population of primordial black holes predating stars. Whatever we find, one truth remains: the universe's oldest monsters still have stories to tell, and we're finally building the tools to listen. Black holes might be more than just cosmic vacuum cleaners. They could be windows into realities beyond our own. The idea that these gravitational monsters might connect to parallel universes or higher dimensions isn't just science fiction. It's a fringe but serious area of physics. At the heart of this speculation is a simple truth: black holes warp space-time so violently that they could be bending the rules of existence itself. When we study the most distant black holes, those relics from the universe's infancy, we're peering into extreme environments where familiar physics breaks down, and the door to the multiverse might creak open just a crack. Take the firewall paradox, a puzzle stemming from Einstein's theories and quantum mechanics. If you fell into a black hole, general relativity says you'd be stretched apart smoothly, while quantum theory says you'd burn up at a searing boundary just inside the event horizon. To reconcile these, some physicists propose that black holes aren't endpoints at all. They're bridges to other universes, with the firewall acting as a dramatic transition point. Distant quasars like ULAS J1342, blazing in the early cosmos, could be testing grounds for these ideas. Their extreme conditions might preserve quantum signatures of higher dimensions or even echoes of collisions with other universes during cosmic inflation. Then there's string theory's wild card, brain worlds. Imagine our universe as a three-dimensional membrane floating in a higher dimensional space. In this model, black holes could be cosmic knots where membranes touch, their gravity leaking into other dimensions. If true, the gravitational waves from ancient black hole mergers like those LISA might detect could carry faint imprints of these hidden dimensions. The quasar J1342+0928, with its bizarrely flickering jets, has already sparked debates about whether its odd behavior hints at extra-dimensional shenanigans. Even more tantalizing is the holographic principle, which suggests all the information in a black hole's volume is encoded on its surface, like a cosmic zip file. If this holds, then distant black holes could be projections of higher dimensional reality, their light carrying encrypted data about alternate universes. The Event Horizon Telescope's snapshots of black hole shadows might already contain clues if we knew how to decode them. Of course, this is all speculative, but that's what makes distant black holes so thrilling. They're natural laboratories for ideas too radical to test on Earth. Every time we discover an ancient quasar defying expectations, it's not just a challenge to astrophysics. It's an invitation to wonder if the universe's oldest monsters are guarding secrets not just about our cosmos, but about all possible cosmoses. And that's a mystery worth chasing to the edge of reality itself. Magnetic fields are the invisible puppet masters of black hole chaos, threads of force so powerful they can whip particles to near light speed and sculpt jets that stretch across entire galaxies. While gravity gets all the attention for pulling matter into oblivion, it's these magnetic fields that often dictate how black holes behave, especially in the distant, high-energy environments of ancient quasars. Picture a black hole not just as a voracious pit, but as a cosmic power plant with magnetic field lines acting like high-voltage wires channeling its energy into the universe. Take the quasar 3C273, whose jets blast outward for hundreds of thousands of light years. Without magnetic fields, those jets would fizzle into diffuse clouds. Instead, they're tightly collimated beams piercing through space like cosmic laser pointers. How, as gas spirals into the black hole's accretion disk, it drags embedded magnetic field lines along with it, twisting them into a frenzied vortex. These wound-up fields act like cosmic railguns, launching charged particles along their lengths at relativistic speeds. The result, jets so precise they can drill through interstellar gas for millions of years without dispersing. But magnetic fields don't just shape jets, they also throttle a black hole's appetite. Simulations of distant quasars like J1342+0928 show that when magnetic pressure builds up in the accretion disk, it can push back against incoming gas, creating turbulent eddies that slow down the feeding process. It's like trying to drink a milkshake through a straw while someone keeps pinching it shut. This magnetic braking effect might explain why some early universe black holes didn't grow as large as expected, despite the dense gas surrounding them. The most extreme magnetic maestros are Blazar's quasars, whose jets happen to point almost directly at Earth. Their light varies wildly in brightness over days or even hours, a flickering that hints at magnetic reconnection events near the black hole. Imagine rubber bands snapping under tension, releasing bursts of energy. That's what happens when magnetic field lines in the disk suddenly break and reconfigure. The Blazar MRKRI@N501 shows these flares in X-rays, each spike likely marking a magnetic storm hotter than the core of a supernova. Yet magnetic fields might also solve one of the biggest puzzles about ancient black holes: how they accelerated particles to such insane energies. The quasar PKS0637-752, observed 9 billion light-years away, has jets emitting gamma rays with energies a trillion times higher than visible light. Ordinary shockwaves can't explain this, but magnetic fields acting as natural particle accelerators can. As electrons spiral along these fields, they radiate energy in a process called synchrotron emission, creating the blinding glow we detect across the cosmos. What's astonishing is that these magnetic imprints might be fossilized clues to the early universe's conditions. The field strength around quasars like ULAS J1342 suggest they were seeded by primordial magnetism, woven into the cosmos during inflation or the first moments after the Big Bang. If so, black holes aren't just monsters, they're historians, preserving a record of forces that shaped the universe long before stars or galaxies even existed. And with telescopes like the Square Kilometre Array now mapping magnetic fields across cosmic time, we're closer than ever to reading that magnetic memoir written in the jets of the universe's oldest black holes. The most violent fireworks in the universe don't come from exploding stars, they erupt from the poles of supermassive black holes, where streams of plasma scream across space at nearly the speed of light. These relativistic jets, some stretching millions of light years, rank among the most energetic phenomena in existence. Yet despite decades of study, how they form remains one of astrophysics' greatest puzzles, especially when we look at ancient quasars like PKS 0637-752, whose jets were already piercing the cosmic darkness when the universe was less than 2 billion years old. At first glance, the ingredients seem simple: a spinning black hole, an accretion disk of superheated gas, and powerful magnetic fields. But the recipe for turning this cosmic stew into focused beams that could vaporize solar systems is anything but straightforward. The leading theory, known as the Blandford-Zenagic process, suggests it starts with the black hole's spin, a rotational energy so intense it twists nearby magnetic field lines into spiraling coils. Picture a dynamo the size of a solar system, where these wound-up magnetic fields act like cosmic rubber bands, snapping particles outward along the black hole's rotation axis with unfathomable force. Yet jets aren't just raw power, they're precision instruments. Observations of the Quasar 3C273 reveal its jets maintain near-perfect collimation across 500,000 light-years, barely spreading despite traveling through the turbulent intergalactic medium. This laser-like focus likely comes from magnetic nozzles in the inner accretion disk, where tightly wound field lines act like the barrel of a gun, channeling chaotic plasma into streamlined beams. Some simulations even show these magnetic structures creating a self-reinforcing feedback loop, where the faster particles move, the stronger the fields become to keep them aligned. But ancient quasars add a twist. Their jets often outshine their modern counterparts by orders of magnitude. The Quasar S50014+813, seen 9 billion years ago, produced gamma-ray flares 1,000 times brighter than any active galaxy today. This disparity hints that early universe black holes had access to superior jet fuel, perhaps denser gas reservoirs or stronger primordial magnetic fields. Others speculate the answer lies in the black holes themselves, younger, faster-spinning monsters with more rotational energy to tap. The real enigma is how particles in these jets reach such insane energies. In galaxy M87, whose supermassive black hole was famously imaged by the Event Horizon Telescope, jet electrons are accelerated to energies 1 trillion times greater than visible light. The same processes scaled up in ancient quasars could explain their mind-boggling luminosity. Magnetic reconnection, think of it as cosmic short-circuiting, may play a role, with snapping field lines launching electron tsunamis. Turbulence in the accretion disk could also act like a natural particle accelerator, slinging matter outward in erratic bursts. What's truly humbling is that these jets aren't just cosmic curiosities, they're universe shapers. As they plow through intergalactic space, they heat surrounding gas, preventing it from cooling into new stars. In galaxy clusters like Perseus, jet-carved cavities in hot gas are visible for millions of light years. Early quasars likely did this on a grander scale, their jets regulating star formation across entire protoclusters. Some theories even suggest these beams could have seeded the large-scale structure of the cosmos, carving channels where galaxies would later form. Yet for all we've pieced together, fundamental mysteries remain. Why do some supermassive black holes produce jets while others stay quiet? How do particles survive the acceleration process without being torn apart? And what explains the bizarre knots and wiggles seen in jets from quasars like J1342+0928? Every answer telescopes give us seems to spawn three new questions, proving that these cosmic particle beams, visible across billions of light years, still guard secrets about the most powerful engines in existence. Dark energy and black holes might seem like cosmic strangers, one silently stretching the fabric of space, the other violently crushing it, but their connection could rewrite the story of the universe. Imagine a force so pervasive it makes up 68% of all existence, yet so enigmatic that we only know it by its fingerprints, the accelerating expansion of the cosmos. Now consider the most distant black holes, those ancient leviathans lurking in the early universe. At first glance, they have nothing to do with dark energy's subtle push until you dig into the numbers and find eerie correlations that hint at something deeper. Take the quasar He 0513-2416, observed 9 billion years ago. Its host galaxy sits at a distance where dark energy's influence was just beginning to overtake gravity's grip on cosmic expansion. Intriguingly, the black hole's growth rate seems to spike around this epoch, almost as if the accelerating universe altered how it fed. Coincidence, maybe. But similar patterns appear in other quasars from this transitional era, suggesting dark energy might have indirectly shaped black hole evolution by altering the flow of gas across cosmic scales. The plot thickens when you examine black hole mergers. Simulations show that as dark energy dominates, it stretches the space between galaxies, reducing the frequency of collisions that funnel fresh gas to central black holes. This could explain why the most distant quasars formed when the universe was denser and mergers were rampant are often more active than their modern counterparts. The quasar pair in protocluster SSDS J0836, for instance, shows signs of a recent merger-fueled feast, something that would be rarer in today's faster expanding cosmos. Dark energy's acceleration might literally be starving black holes over time. Now for the wildest idea, could black holes themselves be sources of dark energy? A controversial theory called the cosmological coupling hypothesis suggests that as black holes grow, their interiors might stretch in sync with the universe's expansion, storing vacuum energy that contributes to dark energy's push. Observations of supermassive black holes in ancient and modern galaxies reveal their masses might align with this model, like cosmic batteries charging as space stretches. If true, the very monsters devouring galaxies could also be fueling the engine that drives them apart. Of course, this is speculative frontier science. Dark energy could just as easily be an unchanging property of space, with no direct link to black holes. But the mere possibility of a connection sends ripples through cosmology. Every time we discover an ultra-distant quasar defying expectations like J1346+0928, whose jets bend oddly in ways that might trace dark energy's influence, we're reminded that the universe's greatest mysteries might not be separate puzzles, but pieces of a grander design we're only beginning to glimpse. Time is the ultimate sculptor of the universe, and even these ancient black holes, seemingly eternal, aren't immune to its slow unraveling. What becomes of a supermassive black hole that's already billions of years old when we spot it? The answer lies in a cosmic tug-of-war between growth and decay, where the universe's expansion battles gravity's relentless grip. Take the quasar SDSS J0100+2802, that 12 billion solar mass behemoth we met earlier. When its light began traveling to us 13 billion years ago, it was gorging on gas at the heart of a young galaxy. but today it's likely a shadow of its former self. As galaxies age, their gas reservoirs dwindle, starving central black holes into a quieter existence. Observations of nearby galaxies show this cycle clearly. Active quasars fade into dormant giants like Sagittarius, a star at the Milky Way's core, emitting only faint X-rays as they nibble on occasional passing stars. The universe's most distant black holes, having feasted in their youth, now face a slow cosmic retirement. Yet dormancy doesn't mean disappearance. Black holes this massive persist for timescales that dwarf the current age of the universe thanks to Hawking radiation, the theoretical process by which they gradually lose mass. But here's the catch: for a supermassive black hole, this evaporation is glacially slow. A typical 10 billion solar mass monster would take 10 to the power of 92 years to fully dissipate, a number so large it exceeds all the atoms in the observable universe. Even the oldest quasars we've spotted are barely middle-aged by these standards. Some meet more dramatic ends. In galaxy clusters like Abell 85, astronomers have found relic radio lobes, ghostly remnants of jets from black holes that ceased activity millions of years ago. These fading signatures hint at cyclical behavior. Black holes might flicker between active and dormant phases as surrounding gas cools and falls inward in fits and starts. The distant quasar H1342+0928 could one day leave similar echoes, its once blazing jets reduced to faint ripples in the cosmic background. But the ultimate fate of these ancient giants ties into the universe's own destiny. In a trillion years, as galaxies drift apart due to dark energy's push, black holes will become increasingly isolated. The last stellar remnants will vanish, and the cosmos will be left with these silent titans orbiting one another in the dark, until even their dance ends in slow-motion mergers. Gravitational wave observatories of the far future might detect these final collisions, the last notes in a symphony that began with the quasar's first light. What's haunting is how little we truly know. The most distant black holes we observe are frozen in time snapshots of their youth. Their present-day selves, having evolved over billions of years, remain just beyond our view. Perhaps some grew even more monstrous, swallowing entire galaxies. Others might have been flung into intergalactic space during cosmic collisions, doomed to wander the void. Each one is a story cut short, its later chapters written in darkness we can't yet pierce, a reminder that even the universe's most enduring monsters are, in the grand scheme, just fleeting players in an epic far larger than we can imagine. Gravity's fingerprints are everywhere in the cosmos, from the delicate spirals of galaxies to the vast, web-like filaments connecting galaxy clusters. But some of the deepest imprints might belong to the universe's oldest black holes, whose chaotic youth could have dictated where galaxies formed or didn't. Imagine these ancient monsters not just as cosmic vacuum cleaners, but as architects, their gravity and radiation carving voids and sparking star formation in ways that still echo across billions of light years. Take the Lyman alpha blobs, enormous clouds of glowing hydrogen spanning hundreds of thousands of light years. These structures, observed in the early universe, often cluster around quasars like SSDS J1342+0928, suggesting their gas was ionized and lit up by the black hole's furious energy output. But the influence runs deeper. Simulations show that quasar radiation could have compressed nearby gas, triggering cascades of star formation in some regions while sterilizing others. It's as if these black holes were cosmic landscapers, sculpting the universe's first neighborhoods with floods of energy and gravitational tides. Then there's the mystery of cosmic voids, massive, empty regions where few galaxies reside. Some, like the Boötes void spanning 300 million light-years, might trace their origins to ancient quasars. How, when a supermassive black hole goes through its quasar phase, its jets and radiation can blow away surrounding gas like a cosmic leaf blower, creating bubbles so devoid of material that star formation becomes impossible for eons. The protocluster around Quasar J0842 shows hints of this, a central void surrounded by a shell of young galaxies, as if the black hole's violence first cleared space, then pushed gas outward where it eventually coalesced into stars. But black holes didn't just clear space, they also built bridges. The cosmic web's filamentary structure, revealed by galaxy surveys, aligns eerily with models where early quasars acted as gravitational anchors. Their immense mass attracted dark matter and gas, forming dense knots along filaments where galaxies would later cluster. The quasar ULAS J1342+0928 sits at one such crossroads, its gravity potentially guiding the flow of material along a filament over 12 billion years ago. Without these black hole lighthouses, the universe's large-scale structure might look entirely different, more scattered, less organized. Perhaps the most startling evidence comes from galaxy clusters like El Gordo, a colliding behemoth 7 billion light-years away. At its core lies not one but multiple supermassive black holes, legacies of ancient quasars whose mergers may have determined the cluster's shape. Their combined gravity likely steered the trajectories of hundreds of smaller galaxies, arranging them into the intricate patterns we see today. It's a cosmic ballet where the heaviest dancers call the shots, their movements choreographed by collisions that happened when the universe was half its current age. Yet the full story remains tantalizingly out of reach. Some regions of the cosmos defy expectations, with galaxies clustering in ways that don't neatly match black hole influence alone. Others show voids far larger than any single quasar could explain. This hints at a grander interplay between black holes, dark matter, and the universe's initial conditions, a recipe we're still deciphering. Every distant quasar we discover adds another piece to the puzzle, revealing how the hungriest objects in existence might have shaped the universe's bones before the first stars finished burning. Their legacy isn't just in the light they emitted, but in the hidden scaffolding they helped build, one gravitational tug at a time. The universe's black holes seem to come in two extremes: stellar mass remnants just a few times heavier than our Sun, and supermassive titans weighing billions of suns. But where are the middleweights, intermediate black holes, those elusive beasts between 1,000 and 100,000 solar masses? Could be the missing link in cosmic evolution, and their absence in the early universe is one of astronomy's most nagging mysteries. These mid-sized monsters matter because they could solve the riddle of how supermassive black holes grew so quickly after the Big Bang. Imagine trying to build a skyscraper without scaffolding, without intermediate black holes merging together. It's nearly impossible to explain how billion solar mass behemoths appeared when the cosmos was barely a toddler. Yet spotting them is like searching for ghosts. Their smaller size means they don't blaze as brightly as quasars, and their gravitational footprints are subtler than their supermassive cousins. That hasn't stopped astronomers from hunting. One promising lead comes from ultra-luminous X-ray sources, or ULK's mysterious objects radiating way more X-rays than a typical stellar black hole should. Some, like the source in galaxy M82, flicker with energies suggesting an intermediate black hole at work, voraciously feeding on a captured star. Others, like ESO 24349's HLX1, beam X-rays equivalent to a few hundred suns, a telltale sign of a mid-sized predator. But confirming their masses is painstaking work, requiring years of tracking the motions of surrounding stars or gas, a near impossible feat for most distant candidates. The early universe complicates the search even further. Intermediate black holes from cosmic dawn would now be ancient relics, possibly lurking dormant in galaxy halos or stripped from their hosts during collisions. But a few tantalizing clues have surfaced. The quasar J1342+0928, observed just 700 million years after the Big Bang, shows chemical fingerprints in its accretion disk that hint at past mergers with intermediate-sized holes. Even stranger, some lensed galaxies from this epoch contain X-ray sources too bright for stellar black holes, but too dim for supermassive ones, potential ghosts of the missing middleweights. Why does this gap persist? One theory suggests intermediate black holes were once common, but their very nature made them fleeting. In the dense environments of young galaxies, they'd have rapidly sunk to the center through dynamical friction, merging into supermassive black holes like snowballs rolling into an avalanche. Others propose they formed differently, not from star collapses, but from direct mergers of dense star clusters, a process that might leave fewer visible traces. The hunt is far from hopeless. Upcoming gravitational wave observatories could catch the ripples from intermediate black hole mergers in the early universe, while the James Webb Space Telescope's infrared eyes might spot their faint accretion flares in primordial galaxies. Each potential sighting is a piece of the puzzle, helping us understand whether the universe skipped a step in building its largest monsters, or if we've just been looking in the wrong light. What's at stake isn't just a cosmic census. If intermediate black holes prove scarce in the early universe, it could mean supermassive black holes grew through exotic shortcuts like direct collapse or dark matter interactions. But if they're hiding in plain sight, their mergers could be the universal assembly line that built the giants we see today. Either way, their story is written in the gaps between the extremes, waiting to be decoded. Before black holes could rule the cosmos, the universe needed stars brave enough to die spectacularly. The first generation of stars, massive, volatile giants called population 3 stars, were the unsung heroes of black hole creation. These primordial behemoths, born from pure hydrogen and helium, lived fast and died violently in supernova explosions that forged the seeds of future supermassive monsters. Unlike modern stars enriched with heavier elements, population 3 stars could grow to staggering sizes, some possibly reaching 300 times the mass of our Sun. Their sheer bulk created extreme pressure in their cores, fusing elements at breakneck speeds and shortening their lifespans to just a few million years. When these cosmic titans finally exhausted their fuel, they didn't fade quietly. Their cores collapsed with such force that even neutron stars, nature's densest ordinary remnants, couldn't withstand the crush. Instead, they imploded directly into black holes with masses dozens or even hundreds of times greater than our Sun. These stellar deaths weren't just collapses, they were cosmic forges. Simulations of early supernova, like those run on the Frontier supercomputer, reveal something startling. Some population 3 stars may have skipped the supernova stage entirely. Under certain conditions, their entire mass could have imploded straight into black holes without the usual explosive fireworks, a phenomenon called direct collapse. This would have dumped pristine raw material hundreds of solar masses worth directly into gravitational traps, giving the universe's first black holes a massive head start. But there's a twist. Not all early supernova created black holes cleanly. Some, like the pair instability supernova observed in models of 150 solar mass stars, would have blown themselves to smithereens, leaving nothing behind. Others may have ejected just enough material to lower their core mass below the black hole threshold. This cosmic lottery meant only the most massive stars in the sweet spot between 25 and 300 solar masses likely birthed the first stellar black holes. Yet even these stellar mass black holes faced challenges. The early universe's sparse gas distribution meant they'd struggle to grow through accretion alone. That's where environment came into play. In dense star-forming regions, black holes could have sinked to the center through dynamical friction, merging with others to form heavier seeds. The protocluster around Quasar J1342+0928 shows chemical signatures hinting at such a merger tree, layers of heavy elements suggesting generations of black hole collisions in its youth. The real game changer, pair instability supernova avoidance. Stars above 300 solar masses might have avoided complete self-detonation due to relativistic effects, collapsing wholly into black holes without the usual explosive losses. In 2021, the gravitational wave detector LIGO spotted a merger involving an 85 solar mass black hole, a weight impossible under normal supernova physics, suggesting it could be a relic from this exotic formation channel. If such monsters were common in the early universe, they'd have turbocharged the growth of supermassive black holes by providing hefty building blocks right from the start. What's astonishing isn't just that these stars died, it's how their death set the stage for everything to come. The heavy elements forged in their final moments seeded future generations of stars and planets, while their black hole remnants became the anchors around which galaxies would grow. Every supermassive black hole we see blazing at the edge of time likely began with a single, catastrophic stellar collapse, a moment when a star's death scream echoed across the universe, leaving behind a gravitational pit that would one day shape the cosmos itself. One of physics' most perplexing puzzles isn't just about black holes, it's about the fundamental nature of reality itself. The black hole information paradox, first posed by Stephen Hawking in the 1970s, cuts to the heart of how we understand space, time, and the preservation of information in the cosmos. At its core is a deceptively simple question. When a black hole devours an object, whether a star, a book, or an entire spaceship, what happens to the information encoded in that object's particles? According to quantum mechanics, information can never truly be destroyed, only scrambled. But black holes, with their inescapable event horizons and eventual evaporation via Hawking radiation, seem to violate this principle. Studying the universe's most distant black holes, those pristine relics from cosmic dawn, might finally give us the tools to crack this paradox wide open. Here's why these ancient monsters are ideal test subjects. Unlike modern black holes, which have spent billions of years interacting with galaxies and absorbing complex mixtures of matter, the earliest black holes formed in a simpler universe. Their surroundings were nearly pure hydrogen and helium, free from the contaminating influence of heavier elements or complex magnetic fields. This purity makes them cosmic laboratories for isolating how black holes fundamentally process information. The Quasar J1342, observed just 690 million years after the Big Bang, offers a glimpse into this pristine environment. Its accretion disk contains unexpectedly sharp spectral lines, chemical fingerprints so clear they suggest information might be preserved in ways our current models can't yet explain. The paradox intensifies when we consider holography, a radical theory suggesting all the information swallowed by a black hole isn't lost but encoded on its two-dimensional event horizon like a cosmic hard drive. For nearby black holes, this information is scrambled beyond recognition by eons of chaotic feeding. But for distant quasars like HLF-S3, which feasted on homogeneous primordial gas, the encoding process might leave cleaner, more decipherable imprints. Some theorists even propose that variations in these ancient black holes Hawking radiation, subtle flickers in their evaporation, could carry echoes of the information they consumed 13 billion years ago. It's like finding a fossil with its DNA miraculously intact. What makes this hunt so urgent is how it bridges quantum mechanics and general relativity. The information paradox is essentially a war between these two foundational theories. Quantum physics insists information must be preserved, while relativity suggests it's irretrievably lost behind the event horizon. Distant black holes, especially those caught in the act of merging, could reveal transitional states where quantum effects dominate gravity's grip. The gravitational waves from collisions like GW 190521, a possible intermediate mass black hole merger, hint at chaotic dynamics where information might briefly leak before being reclaimed by spacetime's fabric. Perhaps the wildest clue comes from string theory's take on the paradox. In models where black holes are tangled knots of vibrating strings, information isn't destroyed but transmuted into higher dimensional vibrations. The light from quasars like ULAS J1342+0928 shows anomalous polarization patterns, twists in its electromagnetic waves that some physicists interpret as evidence of these hidden dimensions. If confirmed, it would mean the universe's oldest black holes aren't just swallowing information but broadcasting it in ways we're only beginning to decode. The implications ripple far beyond astrophysics. If information can escape black holes even partially, it rewrites our understanding of causality, entropy, and the arrow of time itself. Every photon from these distant quasars carries not just the story of the early universe, but potentially the keys to unifying physics' greatest theories. And with telescopes like the James Webb Space Telescope now dissecting the light from the cosmos' first black holes with unprecedented precision, we might be on the verge of solving a paradox that has stumped scientists for half a century, or discovering that the truth is stranger than anything Hawking ever imagined. The holographic principle sounds like science fiction, but it might be the key to understanding reality itself, and distant black holes could be the testing ground. This radical theory suggests that all the information contained within a three-dimensional space like the interior of a black hole is actually encoded on its two-dimensional surface, like a cosmic DVD where a three-dimensional movie is stored on a flat disk. If true, it means the universe might fundamentally operate as a hologram, with our perception of depth being an illusion woven by physics we don't yet fully grasp. Now here's where ancient black holes come in. The most distant quasars, observed just hundreds of millions of years after the Big Bang, offer a rare window into black holes in their simplest, most pristine state. Unlike modern black holes cluttered with complex debris, these early monsters feasted on nearly pure hydrogen and helium, creating cleaner, more predictable interactions where the holographic principle's effects might shine through. The quasar J1342+0928, for instance, shows anomalous fluctuations in its accretion disk, patterns that some physicists argue could be echoes of information being encoded and projected from its event horizon. It's as if we're catching glimpses of reality's underlying code, written in the gravitational waves and light of these ancient giants. But how do you test something as abstract as the universe being a hologram? One approach involves studying the entropy of black holes, a measure of their hidden information. According to the holographic principle, a black hole's entropy should scale with its surface area, not its volume, defying classical thermodynamics. Distant quasars like ULAS J1342, with their simpler environments, provide ideal laboratories for this. Their light spectra reveal unexpected fine structure, subtle quantum imprints that align with models where information is smeared across their horizons rather than buried inside. The most mind-bending evidence might come from black hole mergers. When two black holes collide, their event horizons distort violently before settling into a new, larger horizon. During this process, simulations suggest that information trapped on their surfaces could briefly leak into gravitational waves, ripples in space-time detectable by observatories like LISA. The gravitational wave signal from a merger in the early universe, free from later cosmic interference, might carry holographic fingerprints, telltale oscillations or echoes that betray information scrambling at the horizon's edge. Yet the holographic principle isn't the only explanation for these anomalies. Some physicists argue that quantum entanglement, the eerie connection between particles across vast distances, could mimic holographic effects. Others propose that what we're seeing is evidence of extra dimensions folded into space-time, a cornerstone of string theory. The quasar PKS-0637, with its bizarrely polarized light, might be hinting at this, its photons twisted by higher dimensional geometry near the event horizon. What's at stake isn't just an academic debate. If the holographic principle holds, it would mean that black holes, especially the distant, ancient ones, aren't just objects in the universe but portals to understanding reality's deepest layer. Their event horizons wouldn't just be points of no return, They'd be cosmic projection screens playing back the universe's secrets in a language we're only beginning to decipher. And with telescopes like the James Webb Space Telescope now probing these primordial monsters with unprecedented precision, we might be on the verge of answering a question as old as philosophy itself. Is the universe fundamentally a hologram, and are black holes its most faithful scribes? Studying the universe's most distant black holes isn't just about uncovering the past. It's a window into the cosmos' ultimate fate. These ancient giants, frozen in time billions of years ago, hold clues to how black holes will shape the universe's trajectory over trillions of years. Consider the supermassive black hole in Quasar Ton 618, already weighing 66 billion suns when the universe was young. If monsters like this could form so quickly, what does that mean for the black holes of today, given eons more to grow? The answer might lie in dark energy's accelerating expansion, which is stretching the cosmos apart faster than gravity can pull galaxies together. In the far future, as galaxies drift beyond each other's horizons, black holes could become the last islands of structure in an increasingly empty universe, lonely titans circling one another in the void. But their destiny isn't just isolation. Black holes may also be the universe's final energy source. As gas reserves deplete and stars burn out, hawking radiation, the slow evaporation of black holes could become the last flicker of activity in an otherwise dark cosmos. A supermassive black hole like Sagittarius, a star, would take 10 to the 92nd power years to fully dissipate, outlasting every star in the sky. That's a timescale so vast, it makes the age of the universe so far seem like a single heartbeat. Yet even this decay isn't the end. Some theories suggest that the particles emitted via Hawking radiation could eventually seed a new cosmic cycle, recycling the universe's energy into something entirely unknown. The most startling revelation from distant black holes is how they expose the fragility of cosmic structure. The early universe's dense, chaotic environment allowed black holes to grow rapidly, but today's accelerating expansion means future black holes will lack the same feast of gas and mergers. Observations of ancient quasars like J1342+0928 show how dramatically feeding conditions have changed. Their modern counterparts are starved by comparison. Extrapolate this trend, and the black holes of the far future might exist in a state of perpetual hunger, their growth stunted by the universe's thinning fabric. Yet there's a poetic symmetry here. The same black holes that helped ionize the early universe, carving bubbles of transparency with their radiation, may one day be the last sources of light. In quadrillions of years, when all stars have died and galaxies have faded, the only visible objects might be the glowing remnants of black hole accretion disks, pale imitations of their quasar ancestors, but light nonetheless in an otherwise endless night. Even their mergers, rare as they'll become, could light up the darkness with gravitational waves, the last ripples of structure in a dissolving cosmos. Perhaps the ultimate lesson from these time-traveling giants is that the universe operates in cycles of construction and decay. The black holes we see at 13 billion light-years away were once the dazzling beacons of a young cosmos, shaping galaxies and birthing stars. In the unfathomable future, their descendants might oversee the cosmos' quiet fade to black, not with a bang, but with the slow, inevitable whisper of Hawking radiation. And when even that fades, the universe's story, written in part by these gravitational architects, will reach its final, silent page. From the mind-bending discovery of black holes weighing billions of suns in the universe's toddler years, to their role as cosmic architects shaping galaxies and igniting the first light, these 30 facts have taken us on a journey to the edge of understanding. We've seen how they defy physics by growing faster than thought possible, how their violent jets sculpt the cosmos, and how they might even hold keys to mysteries like dark energy and the holographic nature of reality. Each distant quasar is more than a relic. It's a revolution, forcing us to rewrite the rules of cosmic evolution. Think about what this means. These ancient monsters challenge our most fundamental assumptions about time, gravity, and how structure emerged from the primordial dark. They shouldn't exist at such sizes so early, yet there they blaze in our telescopes, laughing at textbooks. Their light carries whispers from an era when the universe was raw, violent, and untamed, revealing a past far stranger than we ever imagined. And with every new observation, whether it's a super Eddington quasar or a gravitational lens bending light across eons, we're reminded how much we still don't know. So here's the ultimate question. If black holes from the cosmic dawn are already rewriting physics, what other secrets might they be hiding? Could their event horizons encode answers to quantum gravity? Might their mergers reveal hidden dimensions? The more we learn, the clearer it becomes. The universe's oldest black holes aren't just puzzles. They're invitations to explore deeper, think bigger, and question everything. If this journey through space and time has sparked your curiosity, hit like, subscribe, and let us know in the comments what cosmic mystery do you think these distant giants will help solve next. The universe is waiting, and its greatest stories are still untold.